Hello everyone, I am Akshat Joshi and today we are going to be discussing DHCP in terms of configuration, starvation and security. So as the title has already given away, there are going to be three sections. The first one being configuration, which will tell us how a DHCP server can be configured to automatically allocate IP addresses to different clients of a network. Then we have starvation, which basically tells us how an attacker can exhaust the IP pool of a DHCP server. And then finally we have security, which is how and what exactly is port security and how we can implement it to defend ourselves from attacks like DHCP starvation. So let's move on to the first section, which is configuration. And here, for the sake of simplicity, let's imagine a very basic layout of a network consisting of two devices. So both of them will be connected to a switch for a LAN to be formed, and for this local network to communicate with others, we'll put up a router in here. So this is a very simple network that we have come up with. And if we want to configure a DHCP server in it, this is the place where we do it. So essentially the router in this network acts as both the gateway and the DHCP server. Now when we are trying to configure a DHCP server and it has to allocate IP addresses to any new client, along with the IP there are basically four things that are supposed to be allocated to a new device. Out of these four, the first two, which is the IP address and the subnet mask, will be taken care of by the DHCP server itself because it has the pool of the IP addresses, and the default gateway is already configured in the network in the form of the router, so essentially it will be the IP address of the router. So what we can see is that the router in this network takes care of the first three demands that are supposed to be fulfilled, but unfortunately we do not have anything to cover the default DNS server. So to overcome this limitation, what we're going to do is we're going to introduce a new server in this network which will act as a DNS server. And with the layout of the network being very clearly set, let's understand the process of IP allocation from start to end. So let's say there is a new client that connects to this network. The client has to request for an IP address from the DHCP server. But the issue is that the client does not know where the DHCP server is, which the DHCP server is. So the client generates a broadcast packet called DHCP discover, which is sent throughout the network, and when this packet is relayed throughout the network, it is essentially looking for the DHCP server. So to this discover packet, the server responds with a packet called DHCP offer, which is sent back to the client, and keeping in mind that only the DHCP server responds to this discover request. So the offer packet contains the source address of the offer packet will contain the IP address of the DHCP server, and since now the client has the IP, it will generate a request packet, and this request packet will be directly sent to the DHCP server requesting for an IP to be allocated. And then finally the server sends back an ACK or an acknowledgement packet which contains the configuration details or the four details like we just discussed, and these are sent back to the client machine. Once this configuration is sent to the client machine and the process is completed, the server adds an entry in its own ARP table and configures a MAC address corresponding to the IP address that has been allocated. So this exchange of these four specific packets or the process of IP allocation that takes place is called the DORA process of DHCP configuration. And with that, let's move to the second section, which is DHCP starvation. So in starvation, let's say again for the sake of simplicity, let's start with the basic network layout of ours, wherein we have our gateway DHCP server configured on the router and a DNS server sitting in the network. Whenever a new client connects to this network, what will happen is it will start initiate a request for a IP to the DHCP server. Now the point is that the server has a limited pool of IP addresses, so it cannot just go on allocating all IP addresses and everything. So the thing is, a DHCP server identifies its requests, identifies the client based on a address called the MAC address. And let's say for example this is the MAC address of the PC that is requesting the IP. So it will generate a discover packet, the entire DORA process will take place, and once everything is complete, the first IP of the DHCP pool will be allocated to this MAC address. Once that is done, in an ideal case scenario, we imagine that this is where the process stops for this client. But if this machine belongs to an attacker or somebody with a malicious intent, what will happen is they have the option of spoofing the MAC address. So what they'll do is they'll pretend to be a different client and generate the request one more time. And since the DHCP server identifies the client only based on the MAC address, to the server it will look like it is a new request from a different client that is being generated. So again, the DORA process will take place and the second IP will also get allocated to this corresponding MAC address. But what we can observe here is that there is only one client connected to the network. Despite that, there are two IP addresses that have already been allocated. And likewise, this process of spoofing the MAC addresses from the attacker's side will continue till the time all of the IP addresses in the pool of the DHCP server are allocated to the single client machine. And if that is done, this is a very serious situation to be in. Because now what will happen is, let's say there is a new client that connects to the network at this point. Now this client also needs an IP address to be allocated to it, so it will generate a discover packet that will be relayed throughout the network. And the issue here is that the DHCP server has no IP addresses to offer, and hence it will not respond with an offer packet. So what can happen now is that the attacker who has exhausted the DHCP pool may pretend to be a rogue DHCP server and generate a dummy offer packet to give back to this client. This way what will happen is the DORA process takes place between the attacker and the victim. And if the attacker is able to configure the DHCP setting or IP configuration of the victim machine, he has the option of setting the gateway as his own address. So this way all incoming and outgoing traffic of the victim is under the attacker's control. And that is why this starvation is a very serious and very impactful attack, and we need a serious defense mechanism for this. So to look at that, let's move to the third section, which is security. So let's see a defense mechanism for the DHCP starvation attack. The starvation attack is based on the fact that a DHCP server will have to respond to all requests that it gets. The server cannot in any manner ascertain if this is a legitimate request or this is a request with a spoofed MAC address or whatever. So it will by default respond to every request that it gets. And another fact is that the MAC address of a machine can be spoofed as many times as an attacker wants. And these are the two things that make the starvation attack possible. Now the issue is that the DHCP server cannot in any manner understand, or we cannot make the server understand which are legit requests and which are supposed to be a spoofed MAC address requests, and hence we can do nothing to cater to the first point. Hence all we are left with is the second point that we can take care of. And to take care of this MAC address spoofing, what we do is we implement port security. So what port security says is that it limits the number of MAC addresses per switch port. So in a network, when a device connects to the network, it connects to a certain port on the switch. And the switch can be configured in such a manner, like say for example, it allows only 3 different devices on one specific port. And it could get an allocated set of MAC addresses assigned that are allowed to connect to that port. So this way what happens is that if an attacker tries to connect to a port, he generates a request, gets an IP allocated, and now instead of being a different machine, the attacker spoofs his MAC address and pretends to be a different machine. Even that would be allowed only 2 more times. So if the attacker does it more than the times the switch port has allowed, it will generate a violation. Because of which what we do is we end up limiting the number of spoofed MAC addresses. And since we can limit the number of spoofed MAC addresses, it will not end up exhausting the entire pool of the DHCP server, and the other machines that are connecting to the network will be able to easily get their IP addresses allocated. And now that we understand that, let's move to the demonstration of this entire scenario, wherein we'll be discussing 2 tools. The first is Cisco Packet Tracer, which we'll be using to understand DHCP configuration in a network and how we can implement port security on it. And then we'll be using Yersinia to see what exactly DHCP starvation is and how we can perform it over a virtual environment setup. So let's get started with it. So for the demonstration, let's start by booting our Cisco Packet Tracer, and in the Packet Tracer we'll start with a very basic network. So on the routers we'll select 2811, set it up, then we'll add up a switch here which will be 2960, and then on the end devices we'll put up one PC, laptop, and then a server that will act as our DNS server. So let's quickly get all of this connected. Switch to the router, then switch to the DNS, and then both devices. And now first let's go and configure our DNS server. So let's go on services, select DNS and change that to on, and we'll have to configure its IP address, and this has to be a static IP address. So let's say we'll keep this as the IP and let it be on the default subnet mask, which is /24, and the gateway will be the address that we're going to provide to the router, that is 192.168.1.1. And with that, our DNS server is set. We're going to add entries to it later. Now let's configure the router. In the CLI, we'll go and we'll enter the enable mode, then we'll go to configuration terminal. And now what we're going to do here is that first we'll have to go to the interface that is connected to the switch, which is FA0/0. Now here we'll have to provide it the IP address, which is 192.168.1.1 that was given on the DNS server as well. And we'll also have to give it the subnet mask, which is 255.255.255.0. And with that said, now we'll have to apply a no shutdown to change the link state to up. As we can see, the router is turned green, and now after 30 seconds this connection will be established properly. And now on this very interface, to establish a DHCP server, what we'll have to do is, the first command that we're going to be using is IP DHCP pool, and we'll have to assign a name to this pool. Let's say we call it net1, and now we'll have to configure the settings on this DHCP. So if we see the options, there are 2-3 things that we're going to define. The first is network, which will contain the IP and the subnet. Then we have these two settings, which are the default router and the DNS server. So for the first thing, let's go to network and give it the network address, which will be the net ID with the host bits 0 and then the subnet mask. And then next, let's configure the default router, which will be 192.168.1.1. Then finally, let's configure the DNS server, which will be 192.168.1.2. And since this had to be assigned here, hence we had to assign a static IP to the DNS server. So with all of these configurations in place, we have established the DHCP server. And now what is going to happen is, when we typically what we have done is we go to desktop, we go to IP configuration and manually assign all of these 4 fields. But now what we can do is, we can go to the DHCP, it will start requesting an IP address and it will automatically assign, because of the settings that we just configured, it will automatically assign an IP address, give it a subnet mask and enter the default DNS and gateway like we had already configured on the DHCP server. So likewise, let's do it on the other PC as well. We'll go to IP, we'll go to DHCP and it will request an IP and get an IP address. Now just to confirm that all of this works, let's go to the command prompt and try to ping certain things. So let's start with pinging the router. So as we can see, we receive a response from the router. Then we can go ahead and ping the other device on the network and we receive a response from that as well. And the final test will be, we will ping the DNS server, and like we can see, we receive a response from the server as well. So what now we can do is, we'll go to our DNS server and in the services in DNS, let's add 2 records just for the sake of understanding. The first one we'll name router and the IP address will be the IP of the router. So 192.168.1.1, and we'll add this record. Then the next one we'll say DNS and let's assign this the address of the DNS server, which is this. And now that both of these records have been added, what we can do is, on the PC, instead of now writing the IP addresses, what we will be able to do is, we can ping the router and we'll still see that it goes to the correct IP address because of the DNS server resolving the name to the IP. Likewise, we can also test that it will resolve DNS as well. So this is the DHCP configuration, and now let's see how the DHCP starvation works. So for understanding DHCP starvation, what we'll do is we'll take our virtual environment setup, and first let me show you the configuration of the network that we're going to be dealing with. So we have a NAT network set up here, and the IP, that the network address that we'll be working on in CIDR notation is 10.0.2.0/24. So which means that the first 3 octets will be the net ID and the last octet will be the host ID. And as we can see, we have enabled DHCP here. So this will take care of the IP allocation automatically. So in this, let's say the first device that connects to it will be the attacker. So in our case, the attacker is going to be the Kali machine. So we'll boot up this and we'll wait for it to start, and then we'll see that the DHCP automatically allocates it a certain IP. So as we can see, our Kali machine is properly booted up. So what we'll do now is let's quickly see the configuration, and for that let's do an if config, and as we can see here, our IP address is 10.0.2.5, which is the network that we just saw, and this is our subnet mask, which is basically /24 in CIDR notation. And now what we're going to do is let's open up another terminal instance, and we'll switch the user to root. And on this root user, what we'll have to do is we'll install the tool that we're going to use to perform DHCP starvation, which is Yersinia. So for that we'll write apt-get install Yersinia. And while that is running, let's quickly also do another thing. On the previous terminal instance, let's start up MSF console so that we can set up a rogue DHCP server in this Kali Linux, and eventually when a new device will connect to the network, instead of going to the actual DHCP server, it will go to the Kali Linux machine, which is our attacker machine, to get an IP address allocated to it. So while these two things happen, let's wait for a while. So as we can see, our MSF console is booted up, and to create a rogue DHCP server, what we'll do is we'll search for DHCP, and as we can see, this is what we are looking for, the DHCP server. So this is the thing that we're going to use, an auxiliary server. So let's write use3 to set this up, and we'll see what the options are that are to be configured. So we have to configure all of these, and as we can see in the description, there are a certain set of optional parameters that we're not going to configure. So let's quickly set all of the other things up. Okay, so like we can see here, we've configured the rogue DHCP server, wherein it will have the typical broadcast address, wherein this is the network ID, and all the host bits are 255. Then we have our starting and ending of our DHCP pool, where for this rogue server, what we'll do is we'll start IP addresses from 70, and then we'll give addresses till 85. That is the pool we are going to work at. For the DNS server, it is using a default DNS of Google OpenDNS server. And then finally we have the net mask, and the net mask, we've kept it a little different here just for the sake of confirmation that it is this rogue DHCP server which is setting up all the details on the client network. And then finally we have the router and the SRV host. The router is the default gateway address, and the SRV host is the DHCP server address. Both of these will be the address of the attacker PC in this case. So now what we're going to do is, eventually once we have successfully exhausted the IP pool of the default DHCP server, we're going to run our rogue DHCP here. So parallelly, when we go back to our original terminal, we see that the Yersinia has been installed here. So what we can do is we'll go Yersinia-G to start Yersinia in graphical interface mode, and it says that we're using an alpha version. That is not important to us. So this is what Yersenia's interface is, and this is the one that we are concerned about, DHCP. So what we're going to do here is that there is an attack options right here, and the DHCP attacks that we have, there are 4 options, out of which we'll be performing discover packet flooding, and this is a form of a DOS attack, as we can see that the DOS is checked here. So what we'll do is we'll start this attack, and we can see that this very quickly generates multiple discover packets. And if we observe something very interesting, for every packet the source MAC address is a different value. So here we can see that for every packet the source MAC addresses keep changing. So this way it is performing exactly what we discussed, as in it is generating, it's spoofing MAC addresses and then generating multiple discover requests. And since the server will have to respond to all of these requests, it will end up giving away all of its IPs, and then eventually we'll exhaust the DHCP pool. So now we see that I believe enough packets have been already sent to exhaust the pool. So to stop this attack, what we can do is we'll go to list attacks, find our attack, which is the only one running right now, and we'll click on stop here. And with that, as of now, what we understand is that given these number of packets, it is very likely that the pool is already exhausted. And to confirm this, what we're going to do is we're going to connect a new device at this point. So let's say this is our victim machine, which is Windows 11. If this connects to the same network, as we can see, it is connected to the same network called NAT network. And if it connects to the network right now, and before we do that, let's do one more thing here, which is we'll have to run our rogue DHCP server. So as we can see, running background job 0 and starting the DHCP server. So our rogue server is up, which means now if we connect our Windows 11 to this network now, it will not go to the original DHCP server, and it will be configured by our rogue DHCP, which has been manually configured by us right here. So let's check that. Okay, so as we can see, our Windows machine is also properly booted up, and now to confirm the configuration settings, what we'll do is we'll go to our search and we'll look for this setting, which is called view network connections, and we'll boot this up. So as we can see, we have our Ethernet network here, and we're going to look at the configuration settings of this network. So we'll go to our status, and in the status we'll be looking at the details of this configuration from this. And so as we can see here, our IPv4 address is 10.0.2.71, which is the first address of our pool, since remember our pool starts from .70, and then this is the subnet mask, and since this is 2.252 subnet mask, which is the same mask that we have used here, hence we can say that this was indeed configured by our rogue DHCP server. And as we can see here, this is the default gateway, and this is the server address of our DHCP server, and this is the open DNS from Google that we're using because it was configured on our rogue DHCP over here. And this way we can perform starvation attack and then become a rogue DHCP server. So now to defend against this, what we'll do is first let's power off both of these, and now let's get back to our packet tracer to see how we can implement port security and apply a defense to this. So on our packet tracer, what we're going to do is the port security is implemented at the switch level. So we'll go to the switch, and in the switch we'll go to enable mode, then to configuration terminal, and on the configuration terminal, if we see, both of these devices are connected on the ports, on the fast Ethernet ports 0/3 and 0/4. So we'll provide it with an int range of fast Ethernet 0/3 and 4, and we'll be configuring this range all at once. To configure the range, what we're going to do is, first thing that we have to do here is switch port mode access. So this way we are enabling switch port security on it. For that we are going to write another command, which is switch port security, and then now once we have done that, let's start giving it the details that will implement the port security in the end, such as maximum number of devices. So for the time being, for the sake of this example, we'll take that for both of these interfaces there will be only one device allowed on the on the port, and hence we'll set the maximum to 1. Now for the MAC address component, what we can do is there are two options. Let's say first we'll go to the MAC address, and now what we can do is we can manually type in the MAC addresses and hard code them, or the other option is that what we're going to do is the first MAC address is found, because the maximum limit is 1, hence it will look for the first MAC address that is found on this port, and that will become the only MAC address allowed on that port. And to implement that, we have something called sticky. Sticky means that it is only looking for the first MAC address instead of a hard-coded address. And now once all of this is done, we'll have to implement one last thing, which is switch port security violation. And in violation, what we'll do is we'll shut down the port. And once all of this is done, what we can do is, for the time being, let's exit out of this, exit out of the configuration terminal as well. And in order to view our setting, let's say show port security. And as we can see, for fast Ethernet 03 and 04, there is a total of 1 PC that is allowed, and as of now it has found 0 PCs in total, and this is the violation that has been set on both these ports. So for now, what we'll do is, let's say first, in order to identify both of these, let's go to the one of the PCs and then we'll ping the other PC in here. So what we'll do is ping 192.168.1.3. And now what will happen on the switch level is that it will see there is a ping request going from one port address, and it is going to the other port address. Hence it will be able to identify devices on both of these ports. So now if we go back to our switch, on the switch, if we re-enter this port security command, as we can see, it has found a total count of 11 already. So up till now all of this is allowed and there is no violation. Now to execute a violation here, what we'll do is we'll disconnect this device and we'll try and bring in another, say for example, rogue device here, and we'll set this up on the same port as the one previously connected. So its fast Ethernet will be connected to fast Ethernet 03, and we'll wait for this connection to establish, as in we'll wait for the 30-second timeout on the switch, and once it turns green, what we're going to do is we're going to go to desktop IP configuration, and like all other devices on this network, we're going to request for a DHCP IP allocation on this device. So the communication link has turned green, but the the switch does not understand as to there is a different MAC address connected on this port, and that will happen as soon as this PC tries to generate any kind of request to communicate over the network. So let's say it requests for a DHCP packet. The moment it sends a discover, the switch port is already shut down because there is only one device allowed on this port, while this is a second device which is being connected to it. And hence, since DHCP failed, it is being given a temporary dummy IP address, which is an APIPA address. And now to validate that the port will be allowing the original PC to connect, what we'll do is we'll go back, we'll disconnect this, and we'll establish the connection back between this original PC of ours and the port. And as we can see, the port is currently shut down because it has been shut down on the violation level. So what we'll do is to bring this port back up, what we'll have to do is we'll go to configuration terminal, we'll have to go to the port which is fast Ethernet 03, and now there is an interesting thing. If we try and do a no shut, it will still keep the state to down because it is a violation that is occurred. So before we have to turn this back up, we'll have to administratively shut down the port ourselves. So now that we can see, the state is changed to administratively down. And now when we change the state back to up by using no shut, it will change state back to the up. And this way what will happen is the PC will be able to recommunicate again after 30 seconds of interval once the switch establishes that the device is a safe connection. And so now the connection link has turned green, and now what we'll do is we'll try and reconfigure the IP address on this, because this is a new connection now. So if we go back to DHCP, it will generate a new request, and this time it did not deny the request, it still gave it the addresses, because this is a genuine PC which is allowed on the switchboard. And this is how we implement switchboard security, and this way we'll be able to defend from the DHCP starvation attack, because even if this device is an attacker, it cannot spoof its MAC address because it won't be allowed to pretend to be a different PC. And so that will be all for this video. I hope this was very informative and you found it interesting. Thank you so much. We'll meet again.